Okay, it's 8:41. Let's get started. So first of all, course logistics things. For some strange reason, when I uploaded the recording from yesterday to Brightspace, it did not upload with the video, even though I had the video, like it recorded the video and everything. It just didn't upload correctly or whatever. So I re-uploaded it, I think kind of late at night. Uh, and so you will all have an extra 36 hour. Like normally the attendance poll from yesterday would be due today at noon. I'll give everyone an extra 36 hours just to um, have some more time to watch that, since I know I ended up posting it kind of late. Um, yes, that'll be due tomorrow at midnight. Um, and then, of course, the attendance poll from today, which I will create as well, will be due tomorrow at noon, which I guess means that today's is going to be due before yesterday's, but that's fine. That's not the end of the world. Okay. So that's that. There are currently two assignments that you all have to be working on. There's the programming assignment, which is due 2 weeks from yesterday. I see a couple submissions in there already. Looks like people are doing reasonably well so far. There's also a problem set, um, which is due this coming Friday. So uh, take a look at that if you haven't already. I don't think it should be too difficult, but just in case, you might want to set aside an appropriate amount of time for it. And again, remember, for the problem sets, you are encouraged to collaborate and like talk to each other. Just make sure that you like, if you collaborate with other people, just make sure you like indicate that on your submission, so that we're not like freaked out by the fact that two people have the same wrong answer or something like that. Um, and make sure that you do like write your own solution, even if you talk to other people uh, about like working through the problems conceptually or whatever. Um, so yeah, so that is due this coming Friday. There is office hours have officially started. There was office hours this past weekend. I myself will be holding office hours immediately after class. I think I have it listed from 10 to 12, but like I'm not going to wait for 20 minutes before starting it, and it's just going to be in this Zoom room. So if you want to like stick around, you can. If other people join, they can join as well. And I'm happy to help with whatever issues might arise there. Um, I think that's about it. Cool. Yes, that is it. So, um, last week we started talking about big O complexity, specifically like we've got like nested for loops, what the time complexity of those kinds of algorithms looks like. We talked about different uh, like big O functions and how to like think about simplifying one into the other and stuff like that. Yesterday we talked about recursive algorithms and hopefully kind of started to develop an intuition for number one, when and how we can apply a recursive algorithm. Um, how to design that correctly, like how to, given a problem statement, how do we kind of think about breaking this down into something that we could write a recursive program for? And then maybe we sort of started to think about what the complexity of that might look like and things that we can do to mess with that complexity. So today I want to move further along those lines and talk about like analyzing the complexity of recursive algorithms from a more like I guess rigorous perspective. So like specifically given an algorithm, how do we write down an equation that we can then solve to figure out what that complexity looks like? Um, and that's going to lead us into something called the master theorem, which sounds really cool. And it's kind of like it's one of those theorems that once you like digest it a little bit and you kind of understand it, it's like, oh yeah, that's obvious. We don't really need a theorem for that. But hopefully we'll get to that point by today. Um, or hopefully we'll get to that level of understanding by today. Um, If there is more time afterwards, I want to talk a bit more about dynamic programming. So we'll go through an example of uh, an algorithm that we can solve using dynamic programming, and how could we like build up this solution? What does a nice solution look like, and kind of what can we do to like optimize this a little bit further? Um, and then hopefully I will, if I don't mess it up, I'll do some like live coding examples there. Um, so yeah, let's get started. Oh, actually, I guess I should mention the stuff from today's lecture, so the master theorem and the dynamic programming stuff, is not things that were, I think, covered in a ton of detail in past semesters. So if you have like friends who took this class in the past, or if you have friends taking this class in the future, I can't guarantee that it'll be covered. This is sort of stuff that I'm adding here. Um, if you want a reference, this book is fantastic. Let me maybe unblur my screen so you can see it. Intro to Algorithms. I'm going to abbreviate this CLRS because that's the names of the authors, Corman, Leiserson, Rivas, and Stein. There is a like reference to this book in the syllabus as well. It's one of the ones listed there. So you can take a look at that. Uh, I think you can probably find like PDFs or scans of this online or whatever. It is a pretty hefty book, and we're not going to be going through all of it. So you maybe don't want to buy the whole thing. Um, but it's a great book to have. And if you do like grad school in computer science or computer engineering or something, you will almost certainly have like graduate algorithms classes that go through most of this. So that's uh, that's a good reference for today's material if you want to read more about this. And of course, there's always Google and Wikipedia and whatnot. So let's get started. Okay, everyone can see my screen. Okay, here we go. So, as I alluded to, we are going to be talking about the master theorem. I want to motivate this with uh, a problem, a a problem that you might find on like a coding interview, or it might come up, like a version of this problem might come up in practice as a software engineer. You might like see something that you can like reduce to a special case of this problem or something like that. Um, and this is called the maximal subarray problem. And again, if you want to find like a reference for this, it's in section 4.1 of the textbook. Um, but I've taken a few, let's say maybe creative liberties with how to present this. Uh, so let's get into it. What is this problem, right? The scenario. Um, Perfect. Yes, thank you. Link to the PDF. You can take a look at the Zoom chat for a link to that PDF. Great. Yes. All right. So the scenario. I've been watching a lot of Doctor Who, especially because like the new season is currently airing, and it's phenomenal. So this is my Doctor Who version of this scenario. So the Doctor shows up at your doorstep and gives you a notebook with thoughts on the season. I think it's great. I think Gatwa is like still finding his like voice and his character um as the Doctor, but I think it's phenomenal. I'm very excited. Uh we can talk more about this after class if you want. Um yeah, he's great. He's fantastic. Uh I also liked that they brought back Tennant for a couple of episodes. Anyways, I'm not gonna fall down this rabbit hole right now. Okay, the Doctor shows up at your doorstep and gives you a notebook with the prices of a particular stock for the next week. He's a time traveler. He has access to all of this. Um, how can you use this notebook to like maximize your profit, right? Like how can you play the stock market and like maximize your profit, right? So we know that like the thing we care about here is like buying as low as possible and selling as high as possible, right? Buy low, sell high. But of course, we don't have time traveling capabilities, and so we need to find like the pair of low and high numbers that give us the greatest like jump up with the low coming before the high, right? Another way to frame this is, we have like an array of stock prices. We can turn this into an array with like the changes in the stock price and find the subsequence of that array with the maximal sum. Um, so for example, right, let's say he hands us a notebook that says the prices of this particular stock for like one share or whatever is like 7, 11, 5, 8, 7, 12, 11, right? Maybe you can look at this and say like, okay, obviously we should buy at 5 and sell at 12 because that's the best profit we can make. But let's figure this out, right? So we turn this into an array of differences, right? So 7 to 11 is positive 4, 11 to 5 is negative 6. Then we've got 3, negative 1, 5, and negative 1. Thing to note here, there's negatives, right? These are integers, they're not natural numbers. So the maximal subarray problem is really like given an array of integers like this, how do we find the like the contiguous subsequence where the sum of all the elements in that subsequence is maximal? Um, is what a private message? I like rip. Okay, that's fun. Uh, yeah. Anyway, um, yes. Okay. So by inspection, right, we can see that the maximal subsequence here is 3, negative 1, and 5, right? Um, 4 to negative 6 has a sum of negative 2. 4 to negative 6 to 3 has a sum of positive 1. If I look at any other like subsequence, it's not going to give me something as good as 7. So I look at 3, negative 1, and 5. This adds up to 7. This tells me that I should buy at 5 and sell at 12, right? Um, that's a sort of description of the problem. Um, the question is, how do we design an efficient algorithm that computes this, right? So a um, given an array of stock prices or given an array of like differences in stock prices or just given an array of integers, how do we design an efficient algorithm that computes the maximal subsequence? Now, there is a naive approach to this, right? If we just had to write something, we didn't really care about it being efficient, and we really just cared about there being an answer. Uh, what could we do? Does anyone want to like hazard a guess as to what like the most naive algorithm here might look like? We don't put in any like thought into this, just kind of write the first thing that comes to mind, and then what is the complexity of that end up looking like? I'm up 3 points. So the trick is we don't know which things to sum up, right? We need to find a subsequence such that the sum of the elements in that subsequence is as large as possible. Yeah, so calculate for all possible subsequences and find the maximum, right? So we can check every possible pair of buy and sell dates, right? So a subsequence is determined by like where it starts and where it ends. There's n choose 2, O of n squared possible subsequences. And so we can just check every possible pair, right? This is maybe easy enough. Um, but it's O of n squared, which is not the worst. It's not the end of the world. It's polynomial. Would it be better if you buy at 7, sell at 5, than buy at 5, sell at 8, buy at 7, sell at 12? Yeah, okay. So it turns out it turns out that my example is a little bit contrived. We're going to assume that you're allowed to buy once and sell once. Uh, yeah, you're right. It would be better if you only ever like bought like if you bought and sold in a bunch of like increasing quantities. Um, that gives you the best gain. That's how you would play the stock market here. Yeah, for the interest of like correctly motivating this problem, we can buy once and sell once, right? And so we want because otherwise, right, you could look at this subsequence and say, oh yeah, I'll take the 4, the 3, and the 5, and I won't take any of the negatives, and that's great. But that's boring. That's not interesting, right? We're for a data structures class. This is not an economics class. So yes, if you suspend your disbelief just enough to say that we can only buy and sell once, yeah, there's a naive O n squared algorithm, right? Check every possible pair of buy and sell dates. Um, it turns out I'm going to tell you this and hopefully convince you of this in over the course of the next few slides that we can do better. And in particular, we can do better with recursion, right? So recursion, our favorite technique for designing algorithms. We talked about this a little bit yesterday with like Fibonacci and the Towers of Hanoi and all of this stuff. We're going to do a little bit more practice here and try to design a divide and conquer algorithm um, for solving the maximal subarray problem. Okay, so again, the problem statement, given an array of n elements, find the subarray whose elements have a maximal sum. And again, by subarray, I mean like a contiguous like subsequence, right? So I'm not allowed to like break it up. It has to start and end, and all elements between the start and the end point are included. All right, so that's the problem statement. If you remember from yesterday or from just like thinking about recursive algorithms, if we write a recursive program, we need a base case and a recursive case. So what should the base case here be? What's the sort of like trivial input? The input size here is the size of the array, right? N elements. What's the trivial input here? Um, what's the what sort of inputs can we solve this for without really having to think about it? Are we given the size of the subarrays or do they vary? We can choose whatever, we get to pick one subarray of any size. Two elements. Turns out there's an easier one. The entire array, if we have the entire array, there's something like n squared possible subarrays, unless our array is only a single element, right? So there's only one possible subarray, right? Right. So we want to find like what on what input size is this problem trivial, right? What should the base case of our recursion be, right? I guess maybe the way to start thinking about this is like if we're using a divide and conquer approach, then we're probably going to end up dividing the array somehow, right? So the base case should be like when we can no longer divide the array, do we know how to solve the problem? And we can't divide the array any further when there's just one element. And it turns out we know how to solve the problem because there's only one possible answer at that point. And so it's sort of vacuously maximal, right? Um, if there's I guess like the two elements, yeah, if we've got like the stock price for 2 different days, then we have to buy on the first day and sell on the second day. And but there's only one difference. So the array that we're actually looking at only has one element. Yeah, and at that point we return just the unique element of that array, or we just return like the value of the unique elements on that array. Um, okay, so that's our base case. Hopefully I've convinced you of that. Um, the other part of a divide and conquer algorithm is we take our problem and we break it into self-similar, like smaller subproblems, right? So what subproblems does this contain? Um, if we're trying to find a maximal subarray out of n elements, how might we go about breaking this down? One and n minus one. Um, Yeah, so we could do that, right? We could break our array into just looking at the first element and then looking at everything but the first element. If we do this, we're going to have to we're gonna have to break it down n times because every time we're reducing the size by one. The other thing we could do is 0 to midpoint and then the midpoint to n minus one. which is in fact exactly what I was going for. Um, because if we break it in half every time, then we're shrinking the array down a lot faster, and so we're going to end up with a bunch of base cases a lot faster, right? So we can find the midpoint, and then break the array into 0 to mid, and then mid to n. Okay, now if we've broken the array down, how do we actually um, solve our original problem? Well, whatever the maximal subarray happens to be, it's either going to be entirely in the left half, so it's either going to be entirely 0 to mid, or it's going to be entirely in the right half, so mid to end, or it's going to cross over, so it's going to start in the left and end in the right, right? There's three possible options here. Um, does everyone believe me on that? I'll have a figure coming up in a bit, actually. So maybe uh, let's do that. Okay. So a possible way of a possible recursive algorithm that we could write here is recurse on both halves, right? So we take our array, we break it into two pieces, we ask for the maximal subarray on the left half and the maximal subarray on the right half. And then we check all possible like crossing subarrays, right? Uh, as a note, how many of these are there? How many subarrays are there that start on the left and end on the right? Log n? Why do you think it's log n? We're having the array continuously into two each recursion. Yeah, so the depth of our recursion is going to look like log n. I see n squared over two. That's a lot closer. It turns out to be something like n squared over four, right? Because a subarray can be uniquely determined by where it starts and where it ends. We've got n over two options for where it starts because it's going to start in the left half, and then n over two options for where it ends. So it's going to be n over two times n over two, which is n squared over four. It's still O of n squared, right? So there's all possible crossing subarrays that we have to check. But it turns out we can kind of, well, anyway, let's get there in a minute. So we've got three possible options now, right? Our recursive call gives us a subarray that lives on the left half, and then a subarray that lives on the right half. And then we've checked all possible arrays that kind of like cross the middle. And so we've got three possibilities. We just compute the best one out of all three of them and return that. For a visual that maybe I should have put up a little bit earlier, the blue represents our entire array. I've segmented it into the left and the right halves with the light blue and the dark blue. So on the top, you can see that we've got a subarray that lives entirely in the light blue region, and then one that lives entirely in the dark blue region, and then one that starts in the light blue and ends in the dark blue, right? So we'll have like we could break our array into just the light blue, call our algorithm recursively on that, and get back this first like span. Or we could call it recursively, or we will additionally call it recursively on just the dark blue piece and get that span on the right, and then we'll check all of the ones in the middle to get the span in the middle. Right. Now it turns out that there's still like n squared or O of n squared things in the middle. But because we have like a midpoint, we can do a little bit better, and we can sort of accumulate from both ends. Maybe I'll show some code here that maybe helps explain this, right? So I start on here's a bit of code. Lines 2 and 3, I check the base case if or I guess maybe I should explain, like we take a pointer to an array, and then the start and end indices. This is so that we can like slice the array instead of just taking the length of it, right? We can look at like arbitrary slices. If n minus start equals 1, then the slice we're looking at has only one element. So there's only one thing to do. That should say return array of start, but we just return the unique element in that array, and that's fine. Otherwise, we compute the midpoint. We call it recursively. So we look at the array from start to mid, call it recursively on that to get the left best, call it recursively on mid to end to get the right best. And then we do this this thing to compute the like the best possible crossing array. And now I get to use maybe Zoom's whiteboard to draw a picture of this. So let's do that. Okay. The best crossing array, exactly. Yes, that is a very good question that I hope to explain right now. Okay. Can everyone see the whiteboard? Actually, maybe I can just put it here. Okay. So we have an array. Oop. Memento. Maybe this works. There we go. Yeah. Okay. So we have an array that looks like this, and we know our midpoint, right? So what we can do, if I pick a sub array that looks like this, right? The sum of this is going to look like whatever the sum of this half is, right? So if I look at like all the elements that I'm looking at in the left half, I can add them up plus all the elements that I'm looking at in the right half and add them up. And that's going to be the total value of the sub array, right? And it turns out that if I want to maximize this, because I know that I have to start somewhere to the left of this and end somewhere to the right of this, the way to maximize it is by maximizing these two pieces independently, right? So now the problem is a lot easier because now I have something like this. I have a midpoint and I want to find like which set of elements. So I only have like one thing to check, right? Like I only have to like loop through here to find the correct starting index. And let's say for this starting index, I can just add up all of the elements from there to the midpoint and see what that looks like. I can just find whichever starting point gives me the highest value for that sum. And then similarly, for the right half, I can just start at the midpoint, loop through all of the indices in the right half, and then find which index, like for a particular index, I just go from the midpoint to that index and add it up. Yes, exactly. That's now O of n, right? Because now I have n over 2 indices to check here and n over 2 indices to check here. So in fact, it's exactly, there's n steps involved, right? So if I know the midpoint, I don't have to check all n squared possibilities for like the crossing array. So I can compute the crossing array in big O of n time. And it turns out this is sort of where the benefit of the recursive algorithm comes from, right? Because we have we fixed a midpoint, and so we've turned this thing that would normally look like n squared into something that looks like O of n. But of course, now we've got this overhead of the recursion. And so we're going to have to think about what that does to the overall complexity. But hopefully that picture kind of clears things up a little bit. Let me go back to sharing my screen. Okay, everyone can still see the screen? Cool. All right. So yeah, so on lines 5 and 6, we recurse on the left and the right halves. And then the for loop from 8 to 14, we sort of start at the midpoint and then go all the way back to the beginning of the array and just accumulate all of the elements and then find like what index the sum is the best. And then same thing for the right half. We start at the midpoint and go all the way until the end and just accumulate all of the elements and find like at what point the sum is the best. And so we get like the best possible left sum and right sum. The value of that crossing sub array is going to be left sum plus right sum. So we just return the maximum of those three possible values, right? So here's our recursive algorithm. I'll maybe leave it up for a minute so that you can like think about it, try to digest this code, and maybe ask questions if there's like parts of this that don't make sense, because a lot of the rest of this lecture is going to be trying to understand the behavior of this code and trying to understand the complexity of it and stuff like that. So it's important to kind of understand this first, I think. In particular, the questions that I want to try to answer are what does the time and space complexity look like? So yeah, I'll leave it up for a minute. Feel free to ask questions. The subarray from start plus 1 to mid, because that is contained. So if we're assuming here that yeah, the middle thing, right? If it went from like start plus 1 to like mid minus 1, then it would be contained entirely in the left half. So the left recursion would check it. But because it ends at mid, mid is part of the right half because it's like inclusive on the left and exclusive on the right. So like we would go from mid down to start plus 1 on the left sum, and then mid and just stay at mid for the right sum, and that would be like the max. That would be the value of that subarray, and so we would check it there. Oh yeah, so line 5 is the left recursion. The I minus minus is not recursive at all, right? It's specifically checking like we split the array down the middle, and then we kind of like start at the middle and accumulate to the left to find like what elements have the best possible, or like what sequence of elements have the best possible sum. Right. So this is like the extra work that we have to do outside of the recursive calls, because there's this like third case that isn't covered by the recursive cases. These are good questions. I mean, to some extent, you can kind of like take this algorithm on faith. I'm not going to like quiz you on the details of this particular algorithm. Like you're not going to be expected to like produce this from memory. But I think it's important to sort of understand how we took this problem and how we thought about like breaking it down into subproblems and how we thought about designing an algorithm for it, because that skill is one that will be quite important. Um, of course, you can always like memorize a particular algorithm, or you can always like look up a particular algorithm for like a known problem or something like that. But out in the real world, like you'll have things that don't look this clean, and so you'll have to sort of like think about how to break them down and like how to design your own algorithms for it. So if this I guess mostly makes sense, Let's start with the easy question. What's the space complexity? O of n? Why do you say O of n? N elements in the array. Oh, okay. So this is a point that I maybe could have clarified earlier. The array is part of the input, right? So the fact that there's n elements in the array is not part of our like the n elements of the array isn't like auxiliary space that we're using to do our computation. So if we're not allocating anything else besides the array that we take as an input, that doesn't contribute to the space complexity. If we allocated a separate array of the same size and then like used that to like store values in or something like that, then it would be O of n. Yeah, I know we didn't really talk about space complexity that much, so that's a that's a fair thing to assume. O of constant. Okay. Why do you say O of constant? That would be O of one, right? Why do you say O of one? It certainly looks like we're not explicitly allocating extra space here, right? Can it be n squared because of the splitting? So for the space complexity specifically, um, we're not allocating extra space for each array, right? So this is important, right? When we look at the subarrays, one thing we could do is like allocate a subarray, copy the elements over, and then call it on that, like call the thing on the subarray. But because you're right, that would be a lot of extra space that we're using, and in fact, a lot of like extra time complexity because it had this like O of n copying thing. Instead of that, we pass in like the indices, like we just pass in pointers so that we can reuse the same array. Um, so the constant thing is kind of along the right lines because we're not explicitly allocating extra memory here. However, what memory is implicitly being used because this is a recursive algorithm? What memory do we have to account for? The stack, precisely. Yes, you have to account for the stack space. How do we determine the stack space complexity of a recursive algorithm? Like, what does that look like? How much? Uh, what's the maximum number of stack frames that a recursive algorithm is going to use? Right. Remember, every time we have a function call, it's the function call pushes a new frame onto the stack, right? So the maximum number of stack frames is the maximum like number of function calls we'll have going on before any of them return, right? So in general, it's going to look like whatever the maximum depth of the recursion is, right? So I see n over two, I see two to the n, but we kind of talked about this earlier. If every time we split the array into two equal sized pieces, what's the depth going to look like? What's the depth of this recursion going to look like? What do you expect it to look like, I guess? Log n, exactly. Yeah. So the recursive depth is going to be something like log n, and so the space complexity is going to be something like log n because there's going to be log n frames on the stack at the bottom in the base case, right? Time complexity turns out to be a little bit more complicated, and that's basically what we're going to spend the next 20 minutes talking about. Okay, so I guess I'm just going through the algorithm again. Two recursive calls, each on size and over two, and then we've got a big O of n for loop, or we've got like n over 2 and n over 2. So it's like something that looks like big O of n. And then we've got something constant timed, right? There's always going to be three sums that we have to compare. And so it doesn't really matter what that looks like. If there's just three things, right? It's like two if statements or it's whatever it is. It's something constant time. Okay, so if we didn't have this like O of n for loop, we could say, well, we're going to make a bunch of recursive calls all the way down to this like log n thing. And so the depth is going to look like log n. The total number of nodes is going to look like n, or like 2 to the log n, which is something like n. And so we can say that this ends up looking something like O of n. But we've got this extra like O of n loop in the middle, and we can't just multiply it because n changes, right? It's not like every one of the O of n calls to this function are not going to have the same size of for loop on them, right? The ones towards the bottom of the recursion tree are going to have a lot smaller for loops to run through. This is kind of going back to like the if you remember from like yesterday's lecture, there was this like if you're adding two really, really big numbers, then the addition might be log n instead of constant time. But because as you get further and further down, n decreases, it's not necessarily as simple as just multiplying by n, right? Or is multiplying by log n. Okay, so we have to do a little bit more work to figure out what the time complexity of this looks like. Let's try writing down a formula. So let T of n denote the number of steps that our algorithm takes on an input array of size n, right? We're going to define this function T of n, and then we're going to try to understand what T of n actually looks like. So for the base case, T of 1 is just going to be big theta of 1, right? It's going to be bound above and below by a constant because we're just doing the one thing that's just like dereferencing, accessing one index of an array and returning it. Doesn't matter how many steps that takes, that's always a constant number of steps, right? So T of 1 is big theta of 1. For the recursive case, we make two recursive calls, each on an input of size n over 2. And then there's an additional big theta of n for loop, right? So we can think of T of n in the recursive case as being whatever T of n over 2 is. That's the number of steps for one of those recursive calls, multiplied by 2 because we've got two recursive calls, plus theta of n, plus some function that lives in theta of n, right? So something like n. Okay, so here's like a recursive formula for the total number of steps that our algorithm is going to take. The total time complexity is therefore whatever T of n ends up being. But in order to understand this, right, like, is this better than our O of n squared solution? Is it worse? Is it the same, right? How should I expect T of n to grow? This recursive formula isn't really helpful. I need some kind of closed form solution to try to understand this, right? So that's let's talk about that. Let's talk about how to do that, right? Let's talk about deriving recurrence relations, I guess, right? So in general, when you have some kind of recursive algorithm, and you want to understand the time complexity, right? It can be difficult because if you've got a for loop, right? I know the for loop is going to run for n iterations. But if I've got something recursive, then the number of iterations that my program runs for is going to depend on the number of iterations that my program runs for on a smaller input, right? And so you've got this like self-dependence, and so it's not as easy to just like write everything down correctly. And so we use this thing called recurrence relations to kind of like describe it, right? And so in general, the shape of the recurrence relation looks a lot like the shape of the problem or of the algorithm that you've written. So for computing the nth Fibonacci number, T of 1 is a constant, so it's 1. T of 0 is also a constant, so it's 1. And in general, T of n is going to be T of n minus 1 plus T of n minus 2 plus something constant time. And again, this is assuming that addition is constant time, right? If we kind of like hand wave the fact that on an input of size n minus 1 and an input of size n minus 2, it's going to be very, very similar. We get something like T of n looks like 2 times T of n minus 1 plus something constant, right? That's a recurrence relation for Fibonacci. This by itself doesn't tell us that it's big O of 2 to the n, right? But this kind of gives us an equation that we can try to solve and get 2 to the n as an answer. For another example, searching for a value in a sorted array. So this is like a binary search. We'll talk more about binary search with binary search trees, but hopefully this is something that you've seen before. If there's a single element in the array, then it's either that element that element is either the value we care about or it's not. Otherwise, because it's sorted, we split it down the middle, and then we check to see which half our value is going to live in, and then we just recurse on that half of the array, right? So T of 1 is again 1. T of n, given an array of size n, we break it into 2 arrays of size n over 2. We only recurse on one of them, so it's just T of n over 2 plus something constant time, right? So we've got recurrence relations that describe this. Okay. Now, the problem that we're really trying to solve here is, given a recurrence relation, given this like recursive formula for T of n, how do we find a closed form solution? And it turns out, in general, we can't, right? In general, this is very, very difficult because T of n might look really weird. It might depend on itself in like all kinds of crazy ways, and it might just like be very difficult to find an answer, right? There's a couple approaches. One approach, like sometimes we get lucky, right? This is like integrating, right? This is like integrals from calculus, right? Like the vast majority of functions are very difficult to integrate. Like they can't be expressed with like a composition of elementary functions or whatever. A lot of times you get very lucky, and if you're taking a calculus class, you're going to get lucky really, really often in the sense that like a lot of the integrals you'll be given are functions that you know how to compute integrals for. But it ends up being a lot of like pattern matching, and that's sort of what this is going to look like. So one approach is, given our recurrence relation, draw out the recursion tree, right? Stare at it for a while and try to figure out what vibes it gives you. And a lot of times you can just kind of like use your vibes and like heuristics and intuition and stuff to come up with something and be like, oh yeah, I'm convinced that that's the answer. I'm not as interested in this approach for hopefully obvious reasons. The other approach, guess the form of the solution. This is kind of the vibes-based thing, but then we try to prove that it's correct by filling in values of the constants. So for example, for Fibonacci, if we guessed that it looks like big O of 2 to the n, right? We could try to find values of the constants c and n naught such that T of n is bounded by c times 2 to the n for all n greater than n naught. For example, you could use something like proof by induction, right? Find, like, plug in some value of c, show that it holds for n naught, and then show that if it holds for n, it holds for n plus 1 all the way up. And so you kind of take a discrete math class if you want to understand proof by induction. But you could try to prove this, right? We're not going to do that. I'm just throwing that out there as a possibility, right? Similarly, for binary search, we could guess that it's going to look like log n, find our constants, plug them in, and then try to do a proof that shows that our recursive formulation is in fact big O of this thing, right? Crucially, this doesn't actually give us what the actual formula looks like, right? This doesn't tell us what T of n is. This doesn't give us our closed form solution. It gives us an upper bound on the closed form solution. And often that's all we care about, right? This is kind of what I was talking about. Like our function might behave really, really crazy for smaller inputs. But as long as eventually it looks enough like 2 to the n, then 2 to the n is a thing that we care about as far as like determining the big O complexity is concerned, right? So how do we make a good guess? We can do a little bit of pattern matching. In general, if T of n depends on, or if it looks like something like alpha times T of n prime for some like n decreasing to n prime, then we can expect whatever the depth of this recursion is going to be, we can expect the total thing to look something like alpha to the power d, right? If at every step I branch out into alpha different sub recursive calls, and I keep branching out to a depth of d, then I'm going to end up with something like alpha to the power d total recursive calls, right? Alpha might depend on n, d might depend on n, but that's sort of what I might expect the result to look like. If T of n depends on T of n over k, so if in every recursive call I'm dividing the input down into k equal chunks, then we can expect the depth to look something like log base k of n, right? It's going to take something like log of n steps before like dividing by that many, by k to that power or whatever is going to get me down to my base case of just 1, right? That gives us like an estimate for what the depth might look like. If t of n includes a term of theta of f of n somewhere, then we can expect to pick up a factor that looks something like d times f of n, right? If at every step of my recursive call, I'm doing some f of n, some computation that takes f of n time, then I can expect that over all of these recursive calls, I'm going to pick up whatever the depth looks like times f of n at each level, right? So I can kind of expect these terms to show up, and I can kind of try to like use these when crafting an appropriate guess to make, right? So for example, for our binary search, t of n is t of n over 2 plus something constant. We can see that we've got n over 2, and so the depth is going to look like log base 2 of n. If you remember, the base of the logarithm doesn't matter because it's all like it's all off by a constant. So it's just log n. The branching, at every step, we branch into one thing, right? The coefficient in front of the t of n over 2 is 1. So we've got 1 to the log n, which is just 1. The additional term is a constant, so it's going to be d times 1, which is log n times 1. So it's going to give us something like log n. And then, of course, the log n controls the growth of this because it's faster than a constant. Right, so that gives us O of log n as our kind of like guess for binary search. Similarly, for our Fibonacci, we have a depth of something that looks like n because every time we're reducing n by 1, and so it's going to take n steps or maybe n minus 1 steps or something until we get down to our base case. Branching, our branching factor is 2 because at every step we make 2 recursive calls. So we can expect the branching thing here to look like 2 to the d is n, so that looks like 2 to the n. And then we have an additional constant term, so that's going to look something like d times a constant, which is n times a constant, which is something like O of n. And then, of course, 2 to the n dominates n, so the overall complexity ends up looking like O of 2 to the n, which matches what we got for Fibonacci. Now, finally, we can go back to our recurrence relation for our maximal subarray problem, right? We had 2 times t of n over 2 plus theta of n. Okay, so again, we've got a depth. We're having the thing every time. Oh, there is an attendance poll. I fully thought that I would get there. If I don't get there, there's no attendance poll today. Anyway, depth is going to look something like log n because we're having the size of the input every time. The branching factor is going to look like 2 to the depth, which is 2 to the log n, which is something like n. And then the additional term is going to be n times the depth, which is n times log n. So we can expect the overall complexity to be dominated by n log n, right? And so putting it all together, finally, we have this master theorem. Maybe I will get to it. Okay, so this puts together the intuition we've been building into a rule for guessing the form of a solution. And in particular, it gives you a good enough guess that you don't need to worry, like the proof is baked into the proof of the master theorem. So you don't need to prove it. You can just use the master theorem to say, yes, this is what complexity looks like. And it gives you type bounds, which is nice. Consider a general recurrence relation that looks like t of n equals a times t of n over b plus theta of f of n, right? So think of this as a function that spawns a different recursive calls at every step. Each recursive call divides the input size by b, and we do some f of n work to put all of our calls together, right? There's 3 cases to consider. The first one is if f of n is bounded from above by, so we look at the polynomial term we care about is n to the power log base b of a, which is kind of like a to the power 2 to the, or b to the n or something like log base b to the n or whatever. You use your log rules, and that's like that's the polynomial term that's going to dominate from the left side, from a times t of n over b, right? So if f of n is bounded above by a polynomial that's smaller than that, right? So n to the log base b of a minus some epsilon, then f of n is not going to matter, and so our overall complexity is just going to be theta of n to that power, right? If f of n looks like n to that critical power, then we're additionally going to pick up this like log n depth f of n thing, which means that our final result is going to be n to that power times log n, right? If f of n is bounded from below by n to that power plus something, so if f of n is like always polynomially bigger than this sort of critical power, then the polynomial part, the left half, is not going to matter, and so we're going to end up with something that looks like theta of f of n, right? The work that we're doing to put all of this together is going to matter a lot more than the work that we're doing in the recursive calls. That's the master theorem, right? So given a recurrence relation that looks like that, you plug in the values for a and b, you plug in the like n to the log base b of a, and then you figure out which, if any, of the three cases you live in, and then based on that, you know your complexity, right? In particular, the master theorem doesn't apply if the recurrence relation doesn't have the form described above. So for example, for Fibonacci, we're not dividing the input by anything, right? There's no b, we're just going n minus 1 and n minus 2. So we can't use that there. If a or b are not constants, so for example, if it's like, if a depends on n, right? So like if we break it into a different number of recursive calls depending on what our input size is, then a is not a constant, we can't really use this anymore. And then if f of n is not bounded polynomially by n to the log base b of a, right? So it might grow faster than n to that power. It might grow slower than n to that power, but not sufficiently faster, not sufficiently slower. The attendance poll today is, what are some examples of functions that are not like, what are some examples of f of n where you might not be able to use this? Maybe think about that, but not for too long, because I'm going to move on to the last slide because we've got like a minute left in class. Okay, so we use the master theorem to solve our recurrence. I'll go back to the previous slide if people need at the end. But if we use the master theorem to solve our recurrence, our maximum subarray problem has this complexity, 2 times t of n over 2 plus theta of n, right? So if we apply the master theorem, we see a equals 2, that's the coefficient in front of the recursive call. B equals 2, that's the amount that we're dividing the size by every time. And then f of n is n, because that's the extra work that we're doing, is big O of n. Which case applies? So log base b of a is log base 2 of 2, which is 1. So n to the power 1 is just n. F of n is tightly bound by n. It doesn't grow faster or slower than n. So we're in that sort of middle case, which means that we've got the n log n, right? Or we've got the n to the power times log n, which is n to the 1 times log n, which is n log n. And that's exactly what our intuition predicted that this should look like, right? So this maybe serves as like a proof. So we have an n log n algorithm for computing the maximal subarray. That is 9:40. That is the end of class. I'm going to go back to here if people want to take a look at the attendance poll. I forgot to make a thing for it on Brightspace, so I will go and do that now. But that's all I have. If you have questions, feel free to stick around. I have office hours starting, let's say now, until noon. So feel free to stick around, ask questions. Attendance polls are only evaluated based on completion. Yes, you don't need to know an answer to this. Actually, I guess I can give you an answer. Maybe if you want to think about like how to justify this, you can have fun with that. F of n equals n divided by log n is an example of something that's not bound polynomially. Think about why. You did last Tuesday and got a 0. I'll take a look. If you did it, you shouldn't have gotten a 0, unless I specifically gave you a comment. Like if I gave you feedback that explains it, then that would explain it. But I'll take a look. Okay. Would you elaborate on when the C constant would apply? The C constant? Oh, so like f of n might be like 3n or something, right? N to the log. Oh, sorry. That's an epsilon. That's not a C. The idea is if f of n is like n log n, right? And log base b of a, let's say b is 2 and a is 4, right? So log base b of a is log base 2 of 4, which is 2. So it's n squared, right? Um, n log n is not n squared, but n log n is always going to be smaller than n squared, right? So if f of n is n log n, then we don't have to come up with an explicit value for epsilon. We can just say that it's like strictly smaller. Like f of n grows strictly faster or strictly slower than n to the power log base b of a, and that the difference is a polynomial. Master theorem, it's the sort of thing that you get a lot better when you like do a bunch of examples. Next week's problem set will have examples for you to practice with. I am going to stop the recording now.